Hi, and welcome to this presentation on our article on the costs and profits of software defect prediction, which was published in the IEEE Transactions on Software Engineering. My name is Steffen Herbert, and I want to introduce this topic to you today. So let's first recap what defect prediction is about, so the general concept. It's quite simple, actually. If we have some software, it could be a file, it could be a commit, it could be a class, that we put into some model which predicts us as output whether the software is defective or not. And if we get a prediction that it's defective, we can react on this by trying to find and correct this defect. And as a result, we should have fewer post-release defects. What we usually care about and what's usually being evaluated is the question of whether these predictions are correct. But while this is certainly important, this sort of misses part of the point, because you cannot really answer the question whether you actually find these defects, because this would need to take into account whether the quality assurance finds these defects. And even more importantly, you cannot really use this to answer the question whether this is profitable. So do you actually save costs here? Because what's usually considered are standard machine learning metrics, metrics like recall, precision, so how many bugs do I find and how accurate am I, F measure, Massey's correlation coefficient, the area under the curve. Sometimes also metrics that take cost aspects into account, like a variant of the area under the curve where you see lines of code as proxy for the effort, and the bugs found when you invest this effort, you can also look at how many bugs do I find when I check 20% of the code or 80% of the instances. But in the end, if you ask yourself, can I see the profit of my defect prediction model through these metrics? So how much money would my project save if I use this? The clear answer is you don't see it. So this is why we investigated how can we estimate these costs and started to consider what are the cost factors of defect prediction. Because in each of these steps, you have different factors that affect the costs. So for the input and output, this is basically the cost associated with getting and executing a defect prediction model. You somehow must introduce your defect prediction model into your development process, maintain it there, and run the prediction at certain points. Once you get the results, you must react on them. This means you must trigger some additional quality assurance, which you normally don't run, and then correct the defect. This is, again, certain costs you have. And finally, a profit, because you save money because you have already fixed these defects earlier, or the other way around, you still lose something because you missed some defects. So for us, the still losing something perspective is more convenient because it's, well, lets us keep our focus on costs here. You can put all of this together in the formula and just the sum of the cost for initially introducing the model, for executing the model, the quality assurance, and the cost of defects. So let's consider how we get values for these costs. First, the input and output. And if you think about it, it's really a question of the tool market. So consider a defect prediction model that is integrated in GitHub, and it's basically one click and you have it activated for your repository. There's no cost associated with it. If you, on the other hand, have to mine data yourself, find the best model, build some tool around it, introduce it in your CI chain, and so on, and it's very expensive. So we cannot really estimate it. Additionally, these costs are independent of the predictions themselves. So this is convenient because it allows us to just say, okay, these are costs. And once there's a tool market for this, that's the value you can use to estimate this cost. So we focused more on the other costs, the costs for finding and fixing defects, and then also the cost for the defects themselves. So first, finding and fixing. Here we have the quality assurance costs and the correction costs. But if you think about it, the correction costs don't matter. You must correct the defects anyways. Sure, it's more costly to do this later in the development process, basically after the release. But from our perspective, this is part of the cost of the defect. So we can just ignore the cost of the correction, which just leaves us with the cost for quality assurance. And for every software artifact where we run a prediction and we predict as positive, we then have these quality assurance costs and we can just sum it up. Now we have the cost for defects. And here, basically, we have the cost of missed bugs. Missed means it was either not found by a quality assurance or we did not predict an artifact as defective and thereby ignored it. So when we put this together, we have two terms. The first term is just the sum of the costs for defects because we did not predict them. And the second term is the sum of the costs for defects that we did not find with a certain probability with the quality assurance because, let's face it, code review does not find all defects. We can put all of this together in a general cost model. But you might ask yourself now, if you have only cost, why should we use defect prediction at all? Well, we can minimize these costs and we have always costs for development. So we can just try to minimize the costs. And how do we minimize them? Well, by maximizing the profit, basically. And how do we get the profit? Well, we consider trivial models for comparison. So we have basically two trivial models. One would be, let's do additional quality assurance for everything. In that case, our formula basically breaks down to just the quality assurance cost for our software artifacts plus the cost of the defects you still miss because your quality assurance is not perfect. And if you just say, screw additional quality assurance, we keep everything as is, then you just still have the loss through the defects that you have left after the release. We can now compare our general model to these trivial models, for example, for additional quality assurance for everything. And then we see that the profit is basically determined by the costs we're saving by predicting artifacts as not defective and thereby not, for example, reviewing them, minus the costs for running and introducing the model, minus the costs for the defects that we're now missing. So we either miss them because we don't predict them, or even if we don't predict them, it's not all loss because some of them we wouldn't have found anyways. So we need to account for that as well. It's more general in the article, so it's quite complex. But we can basically state how this works for any kind of defect prediction model. But the question is, how do you estimate the quality assurance cost and the cost for a defect? And the problem here is the literature is more or less empty regarding this. So we took pattern from works that's been around for 20 years already, more or less. And there the idea is, let's look at the quality assurance cost per some sort of size unit. It could be per artifact, but we combined them with the later idea that we say quality assurance per line of code. So this is our first part. And since there's no real data on how expensive defects are, we just say we take the mean cost per defect. And because these are usually unknown, we can make it a bit simpler for us and consider them as a ratio. And this is then the defect cost per size unit. So sometimes this is also called the normalized expected costs. So what if you still don't know these normalized these costs? So you still can't compute anything. But because of the mathematical properties, we can prove that our defect prediction model is only better than a trivial model if these conditions are fulfilled. So basically, we can state a mandatory condition that tells us if defect prediction can be profitable, that is driven by the size of the artifact, so the effort for basically reviewing or not reviewing artifacts, and the cost for defects that are predicted, respectively missed. And even if you have only a rough estimation of C, you can use this to determine if the model would likely be cost saving for your project. There's lots more of this and a lot of technical details in the article, so please have a look at it. And if you're interested in the costs of defect prediction or defect prediction in general and want to know more about this, just contact me. Thank you for your attention.
Hello again, and welcome to the Q&A session for the third paper of this session. I'm Robert Felt, and I'm very happy to have Stefan Herbold here, the sole author of this paper. And the paper is called On the Cost and Profit of Software Defect Prediction. And I want to start first by saying I think this is very important work. There are very few studies in software engineering actually looking at cost effectiveness, and many studies focus more on technical evaluation of different approaches, and they compare with some baseline. But when you work with industry and practitioners, what they want to know is what's the actual effect on cost, effort, and so on. So it's very important work. And I'm happy to have Stefan here. And of course, any of you in the audience, please pose any questions you have in the chat, and I will try to discuss them with Stefan. To get things going, maybe I can start a little bit. I know that you discussed this partly in your paper, but I think it's worth discussing. So have you considered how the cost model can be sort of calibrated? Let's say I'm in a company, I'm maybe a project manager or something like that. What should I do if I want to apply this in a project or my company?
So there's two aspects you need to consider. On the one hand, you need to know what kind of quality assurance do you want to then run based on your defect predictions, because they don't tell you where exactly the defect is, only where it might be. So you then need to, for example, run code reviews, and then you should have a rough estimate of the effort for your code reviews that you need to put in. Ideally, you have historic data from your own company, or you ask your developers how much effort they think this would require.
Right.
And on the other hand, you should try to get a rough estimate of the cost of bugs in your company. So, for example, how much effort do you require usually to find these bugs? Are there penalties? How much effort is it to roll out the bug fix late during production? And this will probably give you two very rough estimates, not very, very detailed estimates. I would also suggest that you try to think about lower and upper bounds in both cases. And that way you can basically estimate your best case cost savings by calculating your cost ratio there, and your worst case cost savings. And also see whether you can actually save cost in comparison to just sitting around and doing nothing, or just enforcing, for example, reviews everywhere.
Yeah. Did you also, in this work, consider, or did you show your cost model to practitioners, or did you get some kind of feedback on it, or is that ongoing work?
I talked to some practitioners where we wanted to establish defect prediction in the company, but unfortunately their funding ran out because of an economic crisis of the company. And they had this exact question, basically: how do we know that this would actually benefit us in our process? So how would this save cost for us? Because we don't know how recall or precision, what this would mean here.
Right.
And unfortunately, this stopped before we could actually then implement this there and ask them to maybe estimate such cost ratios. But this was exactly the thing they were asking us when we were telling them this is how we could implement the defect prediction model in your company. And while we were implementing it, unfortunately, the funding on their end ran out. And
I see.
Yeah.
So we have a question from Leandro here. He has a question regarding the cost of correcting bugs, and he's asking, can we really ignore it? Because if the bug is detected very late, the cost for correcting it may be larger than if it's detected earlier, and so on. So, and different approaches used, of course, in the QA might have different effect on this cost. What do you think?
So great question. That's also the question I get always asked regarding this, because that's one of the tricky aspects of the modeling. From my perspective, it's probably always more expensive to fix your bug later. But that's part of the cost of not finding this bug. So that's part of the cost estimation you need to have about letting your bugs go to the release. This might mean that you are cannot change your architecture anymore and need to program around it. So this includes costs for rolling out the bug fix. This might include also contract penalties or maybe even legal fees, depending on what kind of bug you're having. But this is all modeled in this big umbrella of costs of the defects, for which we unfortunately do not have data.
Mm-hmm. Okay, thank you. Another question I had was, so you make, or one of the contributions of the paper is that you have mathematically proven boundary conditions, but what do you consider actually the value of having that? Because I guess in some sense they are dependent on the exact model that you use, so it's not a given that, you know, depending on how realistic or how good a fit the model is to reality. I mean, basically, what's the added value of having the mathematical?
So these boundaries should be mandatory, but likely not sufficient. Mm-hmm. So if you do not find a model that where you have actually a positive size of these boundaries, which happened quite frequently in experiments from us with this model, then this means that your defect prediction model cannot save money under any circumstances in comparison to either doing QA for everything or for nothing. So it's just so far away from being cost saving that you have no possible benefits there. So it allows you to really identify models that are really, really bad. And it also helps you indirectly to estimate how big the range is where you could be cost saving. So the more basically ratios of cost of defects and quality assurance costs you can cover in a cost saving way, the more likely it is that the model would be cost saving for you. And it's also the just by the mathematical properties, the further away your value is from the boundaries, the larger your cost savings. So this is another reason why a larger region and why these cost boundaries are not a pure mathematical exercise, but they actually help you estimate how likely it is to save costs in practice and how much you can save.
No, I agree. I also see value there. My point was more that it somehow depends on the realism of the cost model itself, right? Regardless of the defect prediction model.
Yeah, that's why we say it's mandatory, but likely not sufficient, because we might overlook other costs. We might also overlook some benefits, especially the learning curve of developers. So that's the biggest benefit we're overlooking in there, because they can really learn something while doing code review, for example, or while writing tests about the software, or maybe also find other bugs accidentally. That's, for example, something we did not model. So maybe they prevent bugs in future releases that would not have been found otherwise, maybe even not by users until years later. So it cannot be in our data. So we cannot really model this. But in general, this gives us some guideline of which models are very probably really not good.
Yeah, and I mean, it's like any engineering modeling, right? I mean, you start with some kind of first order approximation, and of course, then you cannot include every interaction and every sort of indirect effect. So that's a little bit how I view it. But you know, in connection to this, what I found when it comes to cost modeling is that it can be quite easy for experts or practitioners or even researchers to come up with many possible factors to put in a cost model. So did you find it like easy to decide on the cost model itself, or which factors to have in there, or was that sort of a tricky decision?
That was quite tricky. It also evolved. So, for example, we have this constant for the execution and the initial cost. And at the beginning, there were like several factors for all of them, but we realized we cannot really estimate any of this. And it's really just what tool vendors do. So we just merged them. And so it evolved over time. We also were considering whether additional factors might be helpful, but then we basically put the boundary at, let's take the direct costs of these models and for now ignore indirect effects like learning curves and so on. So there we might have some bias in there, but at least